Hi, and welcome to the sixth episode of the Sienna training series. I'm Kate Doubleday, and I'll be showing a little bit about time series data formats in Sienna data. Sienna is an open source ecosystem for power system modeling, simulation, and optimization with three main applications. Sienna Data, which we'll be talking about today, focuses on efficient data input, analysis, and transformation. That data can then be used in the other two applications, Sienna Ops, which focuses on system scheduling, including formulating and solving optimization problems like unit commitment, dispatch, and optimal power flow problems. And Sienna Dyne, which enables system transient analysis, including small signal stability and full system dynamic simulations. All three applications are focused on supporting large shares of inverter-based resources in the models, so focusing on wind and solar in particular. And each of these three applications is enabled by a set of packages in the Julia programming language. So today we'll be focused within Sienna data on using the PowerSystems.jl package to represent time series data. So what is time series data used for? First of all, one of the goals of Sienna and the open source framework is to allow you to extend the modeling to capture changes and time varying aspects for any parameter that's important to your model. Using Sienna data, you can attach as much time series data as you wish to any component. If you're using Sienna Ops for simulation, there are also a couple of common and well-established use cases supported in Sienna Ops for certain time series data. So those common use cases include modeling the variability and availability of wind, solar, and hydro, as well as load variability. Another common use case is time varying reserve or ancillary service requirements, where there's a set requirement, but it changes over the course of a day. Beyond these common use cases, part of the value of the flexibility of Sienna is that you can define custom models that use other time varying data as needed. So it's important to note that for some of these time varying parameters, you could either have a single time series that represents a requirement or what actually happened, but you could also have forecasts. And so we're going to talk about representing those two types of time series in Sienna. So the first type of time series is what we call a static or single time series. And the defining characteristic of a single time series is that each time point only has one value. In Sienna, all single time series are currently represented with the single time series type. So a very common static time series format is a column of 8760 values defining the value of a parameter for each hour in a year. Common sources for single time series are requirements, like those reserve requirements we were looking at in this graph, and historical realizations. So either a measurement or some calculated outcome based on measurements for each hour, each 5-minute interval, or something like that in a historical period. The main parameter in defining a single time series is the resolution. So the resolution is the duration of each period where the value is assumed to be held constant. You can pick whatever resolution you like in Sienna. So hourly time series are supported, so are 5-minute, 15-minute, whatever interval makes sense. You might also see the length of a time series listed in Sienna, and that's just the count of the number of time steps in the time series. So this would be a time series of length 24. Type 2 time series are forecasts. And so the difference here is that there might be one value or estimate for each point in time. And a common format is shown here, where we have a different time series windows or runs that start at a certain initial time and move forward through, in this example, 8 steps into the future. Common sources for forecasts include day-ahead weather forecasts. So that could be a 24-hour or 48-hour forecast that has a new forecast window available every day, every 24 hours. Other sources include hour-ahead forecasts or intraday forecasts. And in certain cases, you might have missing data issues, which is quite common, and there might not be historical forecast information available. And so another common source for forecast formatted data is to reformat a single time series, also called a static time series, into this format. And Sienna data offers specific functions to do that reformatting without unnecessary data duplication. So check out the transform single time series function to handle these missing data cases. Within Sienna, there are 3 forecast formats currently supported. Deterministic forecasts are also called point forecasts, and this is a single estimate of what the future value of some parameter will be. So in this case, this is a solar forecast, for example. There's no estimate of uncertainty in the forecast in a deterministic forecast. These examples over here are deterministic forecast formatted data. Another option is a scenarios forecast. So this is a set of possible trajectories. So in this figure, each color is a different trajectory that solar power might take. So this allows for stochastic optimization. Another option is a probabilistic format. And so in this case, each step in a forecast window has a different probability density function or cumulative distribution function. So forecasts have a few more time parameters that are useful to know about. The initial time is the first time point in a forecast window. The interval is the amount of time between subsequent forecast runs. So this has an interval of 30 minutes. Day ahead forecasts often have an interval of 24 hours. Finally, the horizon is the duration of the forecast window. So this is a 1-hour horizon forecast in each forecast run. Within Sienna data, you can store time series either in their sort of natural units, which is often like megawatts for power, or as normalized scaling factors. So here are 2 examples. Here's a time series that's in megawatts, and then here's for example, a load time series that's normalized to peak load, and so it's between 0 and 1. And this is a scaling factor time series format. The benefit of using scaling factors is in storage efficiency. So a single time series, or I should say an individual time series of either a single time series or forecast format can be referenced by multiple components or multiple fields within a component. The data themselves are only saved once, but are referenced by each component or field. And so that makes it for a much more efficient use of storage space, and it's highly reusable across your data set. So look for the scaling factor option and the scaling factor multiplier keywords when using functions like add time series or get time series array. Finally, it's important to note that when you're using scaling factors, the time series of the scaling factor can have the same name as a component field, and this can be a bit confusing. So this is intentional. So this is to represent the relationship between this normalized time series and the absolute magnitude, let's say 10 megawatts that you're using to scale. So by linking those 2 fields when you're defining the time series, the scaling factor time series modulates that component field. And so a very common name that you'll see reused is max active power. So a component like a load can have a parameter, max active power, which might be 10 megawatts. And you can also define a max active power time series scaled between 0 and 1 that will then describe that behavior scaled to 10 megawatts over time. So again, see the various scaling factor fields when defining and retrieving time series data. Finally, a few notes about data storage. This can be useful as you become a more advanced user with time series. There are a variety of ways of optimizing performance with time series data storage. Typically, time series is stored in an HDF5 file that is then linked with your power system. but small time series datasets can be stored in memory for faster performance. Large datasets can be stored in a custom location. By default, this is located in the temp file system. And if you don't have enough storage there, you can choose whatever location has sufficient storage for very large time series datasets. HDF5 compression is not used by default, but it can be customized. Time series can also be defined manually or automatically added from CSV files. So see both the add time series and bulk add time series functions for more information. The system documentation will also help in figuring out the various storage and HDF5 compression options available. Finally, there can be some slowdowns when accessing time series from storage when doing large simulations. So for example, production cost modeling simulations. And so there's an option for caching data in memory for repeated access. And so see the forecast cache or the single time series cache documentation for information about that. Finally, there is a working with time series data tutorial in the PowerSystems.jl documentation that will be included in the video link. So that's a great next step for manually working through adding time series of different formats. So we'll leave it there and look forward to seeing you in the next video.